Hello everyone, we are Group 8 and today we will be presenting our assignment for automatic control and instrumentation. The topic for this presentation is adaptive cruise control, or also known as ACC for short. As modern vehicles become smarter, systems like ACC are playing a bigger role in improving safety, comfort, and driving efficiency. In this presentation, we will walk you through what ACC is, how it works, its advantages and challenges, and the different types available in the automotive industry. Before we dive into the content, allow me to introduce our team. Our group consists of 6 members, and they are Wang Weishuan, Li Kajun, Wang Dejun, Cong Zhenyan, Regan Li Xianglong, and Wang Zihong. Hello everyone. Today I will be introducing you to the concept of adaptive cruise control, or also known as ACC. Adaptive cruise control is an advanced system designed to help vehicles stay within the speed limit while maintaining a safe distance from other cars on the road. It automatically adjusts the car speed, which means the driver don't need to constantly manage the acceleration or braking themselves, especially on highways. Now, let's take a look at some advantages of ACC. First, it significantly enhances road safety as it ensures that the vehicle maintains an appropriate distance from the vehicle ahead. This helps prevent rear-end collision. Second, by actively monitoring the surrounding, ACC system help prevent accidents, especially in traffic-heavy environment. Lastly, its built-in spatial awareness contributes to smoother driving patterns, which in turn help optimize overall traffic flow. Moving on, there are also several types of ACC system. For example, laser-based system, binocular computer vision system, assisting system, multi-sensor system, and predictive system. As shown in the image here, ACC can detect the distance to the car in front and automatically adjust speed to maintain a safe gap, making driving not only easier but also much safer. Thank you.
LCC is developed to achieve three main goals. First, it enhances road safety by automatically adjusting the vehicle's speed to maintain a safe flowing distance. This helps reduce the chances of rear-end collisions. Second, it reduces driver fatigue, especially during long highway trips or in stop-and-go traffic. The system can take over the repetitive speed adjustment so the driver doesn't have to keep braking or accelerating. And lastly, ACC helps improve overall traffic flow by reacting faster and more consistently than human drivers. It can reduce sudden braking and help maintain smoother vehicle spacing on the road. To build an ACC system, we need a combination of smart sensors and control elements. First is the radar sensor, which detects the distance and speed of the vehicle ahead. Then comes the controller, usually a microcontroller or ECU, which processes this radar data and make real-time decisions. Based on these decisions, actuators like throttles and brake actuators adjust the vehicle's speed accordingly. The user display often on the dashboard shows the driver information like target speed and following distance. Lastly, we have the feedback loop, which constantly monitors the vehicle's response and updates the controller, ensuring smooth and adaptive operation.
This flowchart shows how the adaptive cruise control system works step by step. We begin with the start command, which leads to initializing the system. Once the system is ready, the driver can activate the adaptive cruise control system and then set the desired speed. As the vehicle moves, the system continuously monitors traffic conditions and calculates a safe following distance from the vehicle ahead. Based on this distance, it will automatically adjust the vehicle speed to maintain safety. If needed, the driver can override the system, which can then deactivate the adaptive cruise control and bring it to the end. This loop ensures a smooth and safe driving experience with minimal driver effort. Here is the block diagram of our adaptive cruise control system. We start with inputs from the driver and radar. This goes into the adaptive cruise control module, which calculates the desired speed for the vehicle behavior based on speed settings and the distance to the car ahead. The camera system assists by detecting lanes and other road elements, adding visual input for better decision making. The input is passed to the vector control unit, which helps manage motor torque precisely. From there, the inverter converts the control signals into torque. The torque signal goes into a summation point where it's adjusted based on feedback from the current sensor. The corrected torque is then distributed to three PID controllers: throttle, brake, and steering, which fine-tune the actual vehicle response. These control signals are sent to the ECU, which then finally drives the wheels. We also have a vehicle speed sensor providing feedback to the system, and a user display interface that shows current system status to the driver. This closed-loop design ensures the vehicle maintains a safe and following distance, adjusts speed smoothly, and provides partial steering control when needed. Thank you.
So for my part, I'll be talking about the improved block diagram. But before I proceed to show you the schematics of the improved block diagram, I would like to introduce two main components and functions that allow me to enhance further the existing block diagram. One of them will be adaptive radar module, and another one will be a sensor fusion, which is not a component, it is a function. So by introducing both components to the table, what benefit does it provide? For example, of the adaptive radar module, one of the benefits will be increasing precision distance and speed measurement. So it calculates the relative speed and exact distance of the vehicle or obstacle ahead, which is crucial for real-time decision making in adaptive cruise control, which is known as the ACC. Another thing would be enhanced robustness and redundancy. So, for example, it serves as a backup sensor if the camera is obstruct or its data becomes unreliable, thus increasing the safety of the system. Another thing would be to early threat detection. So it helps detect vehicles cutting in or braking suddenly, allowing the system to react faster and more safely. Moving on to the sensor fusion, one of the benefits would be minimizing the potential of false detection. So, merging sensor data eliminates noise or incorrect reading that might occur if only one sensor is used. Another thing would be fusing multiple sensor properties. What it does, what potentially it does is it fuses data from camera system, radar modules, giving a more complete and accurate understanding of the surrounding. And last but not least, it will enhance decision making accuracy. For example, enhances the performance of downstream components like image processing, ACC, or braking system by delivering a trustworthy and validated input. We now move on to the improved schematic block diagram. So, we have introduced two major changes to enhance the sensing and decision making capabilities of the system. It's pretty visible that we have moved the camera system to align with the new data flow structure. Following this, we have added the adaptive radar module as mentioned just now, which serves as a complementary sensor to improve the object detection and decision distance estimation, especially in low visible conditions. By combining the inputs from both the radar and the camera, we have included the sensor fusion block. This block integrates data from both sensors to produce a much more accurate and reliable information, which is then passed through the image processing or the object detection unit for further analysis. For the rest of the control path, which includes the adaptive cruise control, the ACC, the summing point, the ECU, all mentioned beforehand, are fixed. So the add-ons are mostly consist at the beginning of the block graph. Thus, these additions improve the system's redundancy and environmental perception, which are crucial for advanced driver assistance systems.
So in this part, we will be looking into the challenges that the ACC system will face. So the challenge number one is sensor limitations in adverse weather. So one of the most common problems in ACC systems is sensor reliability, especially in bad weather. Rain, fog, or snow can block radar and camera in signals, causing the system to misjudge the distance to other vehicles or even fail to detect them entirely. So to address this, I propose sensor fusion, which means combining input from multiple sensors such as LiDAR, radar, and cameras. Each sensor has their own strengths and weaknesses, so by fusing their data, the system becomes more accurate and robust, especially in difficult conditions. Here's how sensor fusion works. So the radar will provide the long-range detection, while LiDAR gives a detailed 3D mapping, and the camera will interpret traffic signs and lane markings. So a fusion algorithm processes these combined data, which will improve the system's reliability in any weather condition. Now let's move on to another important challenge in adaptive cruise control system, which is the system malfunction or sensor failure. The ACC systems rely heavily on sensors like radar, cameras, and processors to maintain safe vehicle control. But what happens if one of these components fail? So for example, if the front radar becomes blocked by mud or snow, or if there's a camera calibration error, the system might completely shut down, or even behave unpredictably, and even give the driver a vogue warning message. At, at highway speeds, that can be very dangerous. Yeah. So to solve this, we can implement a fault tolerance system with both redundancy and self-diagnostics. Redundancy means using backup sensors or processors that can take over the primary ones when failed. So for example, if the main radar fails, a backup camera or secondary radar can continue to provide data. For self-diagnostics, it constantly monitors the health of all critical components. So if the system detects a failure, it can either hand control back to the driver safely or switch to a safe mode where it limits speed and function while keeping the vehicle stable. So now let's move on to challenge number 3, which is the inability of some ACC systems to detect stationary vehicles, especially at a higher speed. This is a serious issue on highways where a stalled or stopped vehicle might not be recognized in time, which will increase the risk of rear-end collisions. So to address this, we propose using high-definition mapping, which is also known as HD mapping, combined with enhanced object recognition. So the high-definition mapping provides a detailed information about the road layouts and common hazard zones. So when paired with smart object detection, the system can distinguish between moving and stationary obstacles. So even if the sensors momentarily miss the object, the map can warn the system of a potential stop zone, so prompting early deceleration. So this will significantly improve the safety in highway cruising conditions too.
Here's a step-by-step overview of how an adaptive cruise control system operates. First of all, the driver activates the ACC system and sets the desired cruising speed. This starts the control loop of the system. Next, the radar sensor continuously monitors the distance and speed of the vehicle ahead, acting as the system's eyes. To improve accuracy and reliability, the system may combine data from multiple sensors, including radar, cameras, and vehicle speed sensors. These sensors enhance environmental awareness, especially in poor visibility. The electronic control unit, or also known as ECU, process the sensor data and calculates the appropriate response, whether to maintain, reduce, or increase the speed of the car. Based on the ECU's decision, actuator adjusts the throttle, brakes, or steering to maintain a safe following distance. A feedback loop monitors the outcome, such as change in speed or distance, and updates the ECU, ensuring continuous real-time adjustments. Lastly, the system includes safety measures. The driver can override the ACC at any time. An emergency braking will activate automatically if needed. These steps together enable adaptive cruise control to enhance both driving safety and comfort through automated intelligent adjustment. To sum up, adaptive cruise control plays an important role in modern vehicle automation. It enhances route safety, reduces driver fatigue, and also improves traffic flow by maintaining safe distance automatically. Through the use of sensor fusion, the system overcomes challenges like poor weather detection. Additionally, emergency braking system and driver monitoring helps prevent accidents caused by an unexpected obstacles or driver inattention. Our improved block diagram shows how this advanced component can be integrated logically and effectively into a real-world control system. As automotive technology evolves, we expect SCC systems to adopt artificial intelligence, enabling more predictive and adaptive behavior in complex environments.